In this video, we are continuing our midterm review by talking about Lorenz curves and the Gini index. So we are going to look at one of our midterm practice problems. It's question number 4, which I've copied in here. And it says that Lorenz curves in two societies are modeled by these functions, f of x and g of x. And I want to look at part A first. It says compute the Gini index for each of these in terms of the unknown p. So p is some unknown thing, some unknown constant, so p will be in our answer. So I want you to begin by trying these. Pause the video for 2 minutes and try these. 4, 3, 2, 1. Pause that video. Pause it for 2 minutes to really try these on your own first. Alrighty, so hopefully you did that. Let's go ahead and talk about them together. So the Gini index for the function f of x, I'm going to call g subscript f. And remember, the formula for the Gini index is you do 2 times the integral from 0 to 1, and then you do x minus, because remember x was the curve of perfect equity, minus whatever our Lorenz curve is. So our Lorenz curve for f is 4/5 x plus x to the p over 5 dx. Can't forget the parentheses around this because it's minus all of this. Okay, so I need to make sure I distribute that negative sign. So I get 2 times the integral from 0 to 1. And when I distribute this, I can do x minus 4/5 x, which is 1/5 x. And then to the next term, I'll get minus x to the p over 5 dx. So we are now ready to evaluate this integral. Okay, so we have, this is 2. And if I do this antiderivative, the 2 is going to multiply all of it. So this is reverse power rule. I'm going to get x squared, and I divide it by 2. So that'll give me 5 times 2 on the denominator. And then minus, I'll get x to the p plus 1. And then I divide by that new power to get 5 times p plus 1 in the denominator. Bracket, and then I put a vertical line and write 1 and 0 so that I plug them in next. So we have 2 times plugging 1 into this. I'll get 1 over 10 minus, when I do 1 to the p plus 1 power, 1 to any power is just 1. So that I'll have a 1 on the numerator, and then over 5 times p plus 1. And then minus what I get if I plug in 0. If I plug 0 into the first term, 0 squared is 0. So nice. And then 0 to the p plus 1 is also going to be 0. So I'll get minus 0. Close that. Alrighty, so there's one sort of subtle detail that I've neglected to mention here, which I'll come back and talk about it later. It turns out it doesn't matter in terms of the computation, but I'll talk about that later. So this equals 2, and if I simplify this, I get, what am I left with here? Well, actually, no, let me distribute that 2. So 2 times the 10th, that'll give me 1/5. And if I distribute 2 to the next term, I'll get minus 2 over 5 times p plus 1. And if I wanted to combine this into one fraction, I'd get a common denominator, and I can multiply the first fraction on the top and the bottom by p plus 1. So on the top and on the bottom. And doing that, the first fraction becomes p plus 1 over 5 times p plus 1. The second fraction, I have minus 2 over 5 times p plus 1. Okay, and then if I subtract these, we get p plus 1 minus 2, that's p minus 1, and then over 5 times p minus 1. And that's my Gini index for the Lorenz curve f of x. So I could do the same type of thing for g of x. Similarly, so I'm not going to go through the computation because it's really similar to what we just did, almost identical. The Gini index for the function lowercase g, I'll just call this capital G for Gini index, and put a subscript lowercase g for the function lowercase g of x. And it turns out this one equals 4 times p minus 1 over 5 times p plus 1. Okay, so that is the Gini index for this other function. Alrighty, so part B of this question now. which of these, oh, whoops, I realized I kind of gave it away there a little bit. Okay, so let me shift it back to the question so we can read it. So please ignore what I had written there before for the time being. So part B is asking, if you compare your answers in part A, which society is more equitable? So which one would be more equitable? So let's go back to where part B is. And I want you to first pause the video for 1 minute to try this on your own. 4, 3, 2, 1. Pause that video for 1 minute to see if you can determine which one is more equitable. All right, so let's talk about it together. So this one's quicker, which is why I'm just giving 1 minute to think about this. But the key idea is a more equitable society corresponds to one where the Gini index is smaller. So we need a smaller Gini index. Alrighty, and the reason for that is, if I were to draw a picture and I have my axes and I put one here and one here, the curve of perfect equity is the line y equals x. So y equals x, that's the curve of perfect equity. So let me draw some dashed lines here, and now I'm going to draw in two curves. So I'm going to draw one first that's closer to that curve of perfect equity, and the one that's a little bit further away from that curve of perfect equity. So when we compute the Gini index, what we're doing is finding the area between that line y equals x, the perfect equity curve, and our Lorenz curve, whatever it happens to be. And then we're doubling it. That's why we multiply by that 2 in the front. So when we do that, if I look at this purple curve, that area is going to end up being smaller than it is for the orange curve. And by looking at the picture, the purple curve is definitely more equitable than the orange curve. So the moral there is, I need a smaller area, in other words, a smaller Gini index, to get a more equitable distribution. And that's what we said here to start. Okay, so let's compare our two Gini indexes. One was, I guess I should say indices. One was p minus 1 over 5 times. And whoops, I think I miswrote something here. Maybe I just didn't copy down. But this one should have been p minus 1 all over 5 times p plus 1. All right, so good thing I caught that. So 5 times p plus 1. And the other one was 4 times p minus 1 over 5 times p plus 1. So looking at these, the smaller one is the one on the left, because they got the same denominator. They both have the same denominator, but the fraction on the right has a bigger numerator. But this one has a bigger numerator. One thing that I want to note about that is, it would actually be flipped if these fractions were negative quantities. Having a bigger numerator when your whole thing is negative it gives you a smaller number. But in this case, our fractions can't be negative. They can't be negative since a Gini index is supposed to be non-negative. It's in between 0 and 1. So I don't need to worry about that. I'm just going to put this in a bubble. But I did want to point that out. Okay, so we can say our answer now. The society corresponding to the index on the left, so that was F. So the society corresponding to F is more equitable since it has a smaller Gini index. And that is my answer. So I mentioned I wanted to return to talk about a subtle detail in the computation above. So If I didn't include the subtle detail, no worries. It is really a subtle one, but I do want to mention it. So the subtle detail is in this computation, P needs to be greater than 0, it turns out. It turns out that P cannot be, and the reason why has to do with the original Lorenz curve. So in this Lorenz curve, it turns out P has to be greater than 0. And the reason why is that if P was 0, first off, f of x would be 4/5 x plus, and then I'd have something to the 0 power, which is 1. So I'd have 1/5. And if I looked at the graph of that doesn't start at 0, 0. It starts at 0, 1/5. Starts at 0, 1/5, and that's bad. So y-intercept is not 0, 0 here, and that's bad for us. And if P is a negative number, so if P is negative, like P equals -1, we run into a different issue. So if P was -1, we'd get f of x equals 4/5 x plus, we'd get x to the -1/5, which is 1/5x. But the issue is then, if we were to plug a 0 into this, we're supposed to get 0 out. That's a property of a Lorenz curve. But we'd get 0 plus 1/0. And that's undefined. This is undefined. It's not equal to 0 like it needs to be. So because of those issues when P is 0 and P is negative, that's what guarantees that P is a positive value. So if we go up and look at our computation, there's one step where we kind of took it for granted, which is when we plug 0 into x to the P plus 1. If P was something like -2 and you plug 0 in, we would get 0 to the -1 power, which is 1/0, and that's undefined. So we would have run into an undefined issue if P was allowed to be something like -2. But luckily for us, that doesn't happen, because as we just reasoned out, P has to be positive. Okay, so as I mentioned before, this is really, really subtle. I would not expect you to write any of this if you had a question like this on a test. I wanted to mention it in the videos because one of our course goals is really mastering the content. So I want to really point out the subtle details that could appear. Alrighty, so that is it for this video. In the next review video, we will talk about consumer and producer surplus.